Hey everyone. So in this video, I'd like to talk about equations and graphs and really develop more of the relationship between the two. And so we've already had some experience building graphs from equations, but let's do another example just to have something to refer to. And so here it says fill out the table for the equation p is equal to 8 minus c and use the table to graph the equation. So we're not given a table, we're not given any values to start with, so we just have to make a table on our own. And so here I'm going to go ahead and start building that table. And so the first question we encounter is, what's our first variable, what's our second variable? And usually this variable that's sort of on its own, the variable we can kind of compute values for, that's the second variable. And usually this variable that it's sort of on the side with more of an expression going on for it, that's usually the first variable, right? We can kind of plug in values into this variable c here, do some computation, and we'll know the values of the variable p. Right, so here I'm going to have my left column be my c values and my right column be my p values. And again, we're not given any values to start with for c like we usually are. So here, let's just pick some values that might be nice to plug into this equation for c. So I'm just going to pick some numbers here, 0, 1, 2, 3, 4, and 5. I think that'll give us a good sense of how this equation works. And so we've already had some experience with this, but let's get some more practice. So if we want to determine the corresponding value of p when c is equal to 0, well, we just plug that value of c into the equation, right? So here we have p is equal to 8 minus, well here in this case we're talking about c being 0 if we're trying to find the corresponding p value. So I'm going to write 8 minus 0, and 8 minus 0 is 8, so p is equal to 8. And again, this is specific to when we're letting c equal 0. Right, so p is equal to 8. And then if we do the next example, we can just plug in c is equal to 1. So 8 minus, when c is equal to 1, we get p is equal to 7. And again, just to emphasize that here p is not always equal to 7. It's only equal to 7 specifically when we're saying c is equal to 1. Right, and we can kind of go through more of this. Maybe I'll just do one more example. P is equal to 8 minus 2. Well, here we get p is equal to 6, specifically when c is equal to 2. And we can see that here we just subtract away 3 from 8 for the next example to get 5, 4 from 8 in the next example to get 4, 5 from 8 in the next example to get 3. And we can kind of see this list of pairs of numbers that make our equation true. Right, and so here, in all these examples, what do? We pick numbers for c and we plug them in and we figure out the corresponding values for p. And so here, in some sense, I'll write this off to the side here. So in some sense, we are inputting values in for our c variable, our first variable, and the p values, right, these are the results that we get out from our equation. So sometimes we think of these as outputs. Okay, so I guess I missed a word in here. Let me erase this. So, and the p values are outputs of our equation, right? So here, usually when we're dealing with an equation with two variables, and it's sort of set up in this format where one of the variables is alone, we think of it as a second variable, and one of the variables is more in this expression, we think of it as a first variable. We like to call that first variable the input variable. Right, we're inputting values into this variable, and what we get out in our second variable, we like to think of as our output variable. So sometimes you'll hear variables and equations referred to in this way in terms of inputs and outputs. Okay, so now let's use this table here to make a graph for this equation. So here I've already made two axes below, right? So here we have our horizontal axis. And this is usually for our first variable, also usually we'll think of as our input variable axis. And so in this case, that's C, right? So I'll label that right here. And then above, we have our vertical axis. Right, and this is our output variable axis. Right, so in this case, that's P. And so we don't have, maybe I'll put the C beside our axis just to make it kind of symmetric. Okay, so here we don't have the axes tick marked like we usually do, but if we look back up at our table, we see that the values of P seem to go as high as 8 in this case, just from our examples that we've computed. And then here for our values of C, well, they seem to go as high as 5, start at 0, but maybe it might be worthwhile to include a little bit more here. So here maybe I'll just label them both. I'll make them go as far as 10. And then here I want to make tick marks in my axes so that they're evenly spaced out. Right, so here maybe the halfway mark should be, I think that's about halfway. That should be where 5 is along my horizontal axis, and similarly here, that's where 5 should be for my vertical axis. Actually, maybe I can make that a little bit lower. And then here we want to just make sure everything else is evenly spaced along the way, include the smaller tick marks, and so here I'm going to go in increments of 1, so here I think that's a nice way to split up 5 cleanly, and then here we've got 6, 7, 8, 9, and I think those are evenly spaced as well. Maybe let's try this again. I always find this challenging to cut up 5 evenly. But here just know that each of those tick marks are meant to be one further along our axis, and really we want them to be evenly spaced. That's probably the most important thing you do when you're dealing with making graphs and grids, is you want your tick marks to be evenly spaced, and they're there to represent the same change in values along your axes. Okay, and so here what we do is we're going to plot our points from our pairs of numbers from our table. And so here, maybe just as another example, as a reminder, if we take the pair 2 and 6, right, 2 for C and 6 for P, how does that look on this grid? Well, here I'm looking at a C value of 2 and a P value of 6. That's here, right? Together, this is the pair of numbers 2 for C and 6 for P. So let's do that for our other points from our table, right? So here we've got 0 and 8 together. So 0 for C, 8 for P, right? If I look at, here's the point 0 for C and 8 for P, right? Because there, if I look to my P axis, I'm at the position 8, and if I look to my C axis, I'm at the position 0. And similarly, we have the pair 1 and 7, right? So here, that's this point here. Because if I look down to my C axis, I'm at 1, and if I look to my P axis, I'm at 7. Here we have 3 and 5. And we have 4 and 4, 5 and 3, 6 and 2, 7 and 1, and 8 and 0. Actually, we didn't list those out, but we can check that those would be values that would make the equation true. And so here, when we want to sketch the graph of our equation, to graph, right, one thing we want to do is we want to plot several points. And so we've done that here. We've taken points from our table, the pairs in our table, and we've put them down as little points on our grid. We've located where they should land on our grid, so that's what we mean when we say plot these points. And then next thing we want to do is we want to sketch a smooth curve through the points. Right, so here in this case, a smooth curve, I just mean not like zigzagged or anything, not with corners. Here, if I draw a smooth curve through these points, I get this straight line. It's not always going to be the case that you get a straight line, but in this case we do. And so here, this straight line, this is what we call the graph of, in this case it was p is equal to 8 minus c. So hopefully this feels very familiar to you. We talked about this in a previous video, but there's actually some language I want to introduce as we use graphs more and more. Right? So here, if we look at each of these, any of these points on the graph, maybe let's just start with the one that we've sort of emphasized a little bit in this graph. The point has a horizontal and a vertical position. Right? So each point on a graph has a horizontal and vertical position. And so here, this horizontal position, this vertical position, we call these coordinates. And so, in the above example, here we circle this point with the c value of 2 and a p value of 6. Well, that horizontal position, we said that horizontal coordinate is 2, right? So for our point above, the horizontal coordinate is 2, and the vertical coordinate, the position of the point relative to the vertical axis, this is 6 in that case. And so together, these two numbers, they form the position of the point. And then usually, if we want to refer to this point, we write this as an ordered pair to refer to the point with a horizontal coordinate of 2 and a vertical coordinate of 6. We write that as the horizontal coordinate first, then the vertical coordinate second, in between parentheses. So here, maybe I'll write that down more generally first, and then I'll write it down precisely. So here, if we want to refer to that point, we write down the horizontal coordinate followed by the vertical coordinate, we separate these two things with the comma and wrap them in parentheses. So if you see a pair of numbers in parentheses separated by a comma, this is talking about a position on a grid, where that first quantity is the horizontal position, the horizontal coordinate, and that second quantity, that second number, that's the vertical coordinate. And so here, our above example, right, this is also, this is seen as 2, 6 in parentheses. And so let's say, we look back up at our graph, and we have all these points that we see. What if we take, let's say this point here? How would we label this point in the way we described below? Well, here its horizontal coordinate is 5, its vertical coordinate is 3, and so here this is the point 5, 3, right? Horizontal coordinate first, vertical coordinate second, wrapped in parentheses and separated by a comma. And so here, one thing I want to emphasize is sometimes you'll hear this referred to as an ordered pair. When people say ordered pair, they're just talking about points on a graph. And there's another meaning we'll describe in a moment. Sometimes we also thought of as solutions to an equation. We'll explain why that's the case. But here, these are called ordered pairs because really, they're a pair of numbers and they're ordered. The first one always means horizontal coordinate. The second one always means vertical coordinate. We can't change the two. Right? If we go back up to our graph up here, the point 5, 3 is different from the point 3, 5. Right? What's the point 3, 5? Well, that's this point right here. Right? This is the point 3, 5 because here, if we start at the horizontal coordinate of 3 and the vertical coordinate of 5, we see that that's where the point would be located. So the order of these numbers matters. That's why they're called an ordered pair. So why do we care so much about graphing? Well, graphs are a great way to visualize an equation. So here, that's a pretty important idea. Let me write that down. So graphs are a way of visualizing equations. Right, so earlier we started with an equation. We found some pairs of numbers that make that equation true, and we plotted those points out onto some grid and sketched the curve that ran through those points. So the points on the graph, are the values that make the equation true. Right, so for example, we had the point 3, 5 above on our equation, above on our graph earlier. Right, so here, this point 3, 5, this meant that here we had c was equal to 3, and p, our output variable, this was equal to 5. And notice that this is a point, it's on our graph, but it also makes our equation true, these values, right? So here, if I let p be 5, right, we start with the equation p is equal to 8 minus c. If we replace p with that value 5 and c with the value 3, is this equation true? Well, 8 minus 3 is equal to 5, so it is true. Right, so here I don't need to really put a question mark here. It is true. And so this point being on the graph is really associated with the fact that it makes the equation true. That's why we can kind of see the graph as a visualization of the equation. And this also goes the other way, right? So here the point's not on the graph. So the point's not on the graph of an equation. These points don't make the equation true. So if we go back up to our graph above and we look for a point that's not on the graph, maybe I'll identify this point 5, 6, right? So this is a point, it's not on the graph of our equation, that point 5, 6. Actually, no, this is position at 5, 5. I'll put it a little bit higher. This is 5, 6. So if we take this point, not on the graph of our equation, and we try to plug it into our equation, and so here I'm going to write it down. This is 5, 6 is what we started with, and if we plug it into our equation, p is equal to 8 minus c. In other words, here we're saying that we're letting c be equal to 5, p be equal to 6. And notice that this doesn't make our equation true, right? I plug in 6 for p, I have equals 8 minus c, 8 minus 5, and I ask, does this make my equation true? Well, 8 minus 5 is 3, and that's not the same as 6, right? Here, this is 6 is equal to 3. That's not the case. And so here we can see that points that don't lie on the graph of our equation, they don't make the equation true. Points that do lie on the graph, they do make the equation true. And so this is really one way we can see that graphs are a way of visualizing equations. Here, so maybe let me add a little bit more language into this. So here, usually we say, if an ordered pair makes an equation true, an ordered pair that makes an equation true, when we plug that ordered pair into the equation, if it makes the left side the same as the right side, it's making the equation true. An ordered pair that does this is called a solution to the equation. And so here, when we're looking back up, and we saw that this ordered pair, 3, 5, it made the equation true. When I plugged in 3 for the first variable, 5 for the second variable, the output variable, it made the left side equal to the right side of the equation. It made the equation true. Here, this means that this point is a solution to the equation P is equal to 8 minus C. And then here, if we look back at the pair 5, 6, what we're saying is that this is not a solution, does not make the equation true, not a solution to the equation P is equal to 8 minus C. And so when we say graphs are a way of visualizing equations, what we're really meaning is that graphs show all of the solutions to the equation. Points on the graph are solutions to the equation, points not on the graph, they're not solutions to the equation. And so this is a big idea in mathematics. You'll learn about a lot of different kinds of equations, and for each kind you'll also learn about its corresponding graph. And so here, all this language and all these ideas you'll see over and over and again. So let's continue practicing these ideas and getting used to this new language. So here I have an example. It says, determine whether the ordered pairs below are solutions to the equation y is equal to 3 over 4x. So I have 3 ordered pairs. We want to check if they're solutions to our equation. And I definitely encourage you to pause the video at this point and see if you can try and work through these examples first yourself, and then we can go over them together. So the first big question that we ought to ask is, here we have an ordered pair, we have multiple ordered pairs, and one quantity is meant to represent one variable, and the other quantity is meant to be replaced into the other variable. Now, which quantity goes with which variable? And so here, this y variable that's alone, we can think of this as our output variable or a second variable. Right? Usually, we think of this first variable, this input variable, as a variable that goes with the expression that we're going to evaluate. And then the output variable, that's the variable that's isolated that we can just sort of compute from the expression on the right. And so here, in each of these ordered pairs, we can think of this first number as the x variable and the second number as the y variable based on our equation and how it's written out. And so here, if we want to figure out whether or not these ordered pairs are solutions, we just want to check if these pairs make the equation true when we plug them into the equation. So here, I'm going to take our equation, y is equal to 3 over 4x, and I'm going to replace x with 8. And y with 6. And I want to ask the question, I know I'm writing an equality sign here, but we don't know if really this left side is going to come out to the same value as the right side. So I'm going to put a question mark there. And so we want to evaluate the right-hand side and see if we get 6, so that we can verify that the left and right side are equal, and then we'll know that that's truly a solution to the equation, this ordered pair. So here, let's multiply out this right-hand side. How do we multiply a fraction with 8? Well, here I can write 8 as the fraction 8 over 1. Right? So here we have 8 over 1, that's being multiplied with 3 over 4. And so how do we multiply fractions? Well, we just multiply straight across, right? Numerator to numerator, denominator to denominator. We get 3 times 8 is 24, over 4 times 1, that's 4. And so 24 divided by 4, well, that's 6. And so this is true, right? 6 is equal to 6. And so what this is saying is that when we plugged in this ordered pair 8, 6 into our equation, the result was true, the equation was true. And so this point here, it is a solution to our equation. Another thing that this means is that if we were to graph our equation, this point would be on the graph. So let's do the same thing for the point 2, 3, right? So here I'm going to plug in 2 for x, 2 for our input variable, 3 for our output variable, and I'm going to ask, does it make our equation true? Well, again, we can multiply 3 over 4 by 2, and so this is the same as 3 over 4 times 2 over 1. And so 3 over 4 times 2 over 1, that's 6 over 4. And 6 over 4, I can reduce this, right? So here, if I take this fraction and I divide the top and the bottom by 2, right? Every fraction is the same as one we can obtain by dividing the same number to the top and the bottom. So I can reduce this fraction to the new fraction 3 over 2, and it's equivalent. But, right, this is not the same. The left side is not the same as the right side in this example. So here, this ordered pair, 2, 3, it is not a solution to our equation y is equal to 3 over 4x. And let's do this last example here. Again, I'm going to replace my x variable with 6. I'm going to replace my y variable with 9 over 2, and I'm going to ask, is this equation true? And so here I'm going to multiply that right-hand side. So 3 over 4 times 6 over 1. This is equal to, well, is this equal to? It's more of a question. 9 over 2. And so on the left we have 9 over 2. On the right we have 18 over 4. And again, we can reduce this fraction on the right. Right? Both the top and the bottom of this fraction are divisible by 2. And so that comes out to be 9 over 2 on the right, 9 over 2 on the left. And really, this ordered pair does make our equation true, right? The left side comes out to the same value as the right side. And so again, we checked all these ordered pairs, we've determined whether they are solutions or not to this equation, and this is also telling us whether these are points on the graph. We didn't graph out this equation, but now we know some points that are on the equation and not, or on the graph and not on the graph of this equation. So in this next example, we're given the graph of some equation. Right? We don't have that equation, we're not given an equation, but we're given the graph of some equation. And we want to determine whether or not each of these 3 ordered pairs is a solution to the equation. And so remember that solutions to an equation, these are the points we see on the graph. And so if we can see this ordered pair on the graph, that's really meaning that that ordered pair is a solution to the equation. Even though we don't know it, we don't have the equation, we can't plug it in, we know if it's on the graph, it means that it is a solution to the equation of the graph. And so here let's take this equation 4, 2 and ask if it's on the graph. And if it is, that means it's a solution to the equation. It would make the equation true, whatever it is, when we plug it in. And so here, again, this 4, this first number, that's the horizontal coordinate of our point, and 2 is the vertical coordinate of our point. Maybe I'll write these down, right? So here, this is the horizontal coordinate. Here 2, the second value, it's the vertical coordinate. And so here, if I look at the horizontal coordinate of 4 and the vertical coordinate of 2, they meet up at this point here. And this point is on the curve. So it is on the graph. This means that it would make the equation true. Right? It is a solution to the equation. So yes, this is a solution. And in particular, it's a solution to the equation of the graph. Okay, what about 6, 2? Well, here I go up to 6, and I look at a height of 2. And that's not a point on the graph, right? So here, this is not a point on our curve. It does not make our equation true. This is not a solution. And if I look at, the reverse of this, if I look at the point 2, 6, actually this is a solution, right? If I look at 2, 6, right, this point is on the graph, it is a solution. So here maybe I'll write down, just to emphasize that, this is an ordered pair and the order does matter. So 2, 6 is a solution, though 6, 2 is not. These really refer to different locations on our grid. And then 7, 11. So 7, maybe I'll erase some stuff on our grid so it's not so cluttered. So here, if I go to 7, 11, I look at 7 as a horizontal position, and then I look at 11 as a vertical position. These two meet at this point here, and this is a point on our curve, and so this is a solution to the equation, whatever it is. I don't know the equation, but I know that this point is a solution. If I plug in 7 for the first variable, the input variable, and 11 for the output variable, our equation would be true, whatever it is. So let's take a look at one last example here. It says, below is a graph showing how far Corey's vehicle can drive, D, in terms of the amount of gas, G, in the tank. So we're given two varying quantities, how far Corey's vehicle can drive, and the amount of gas in the tank. And we're also told the letters being used to represent these varying values. So D for how far the vehicle can drive, and G for the amount of gas in the tank. So here's the graph. Usually when we're given a graph, the horizontal axis and the vertical axis are usually labeled with what variable they're representing or telling us quantities for. And so here I'll do that now. I'll say that G is there to correspond to our horizontal axis, the amount of gas in the tank, and D, the distance that the vehicle travels, that's going to correspond to our vertical axis. And so I'd like to emphasize or highlight one thing in the situation statement, is this phrase, in terms of. So you'll see this phrase a lot as you go through your different math classes. So in terms of is usually telling us what our input variable is going to be, what our input quantity is going to be. And so here, the quantity that follows in terms of the amount of gas in the tank, that's telling us that really that's our input variable. That's the variable we can use to determine the other variable. Right? If we know the amount of gas in the tank, we can use that to determine how far Corey's vehicle can drive. And so here, this other variable, before the phrase in terms of, that's usually our output variable, the quantity we're thinking of as our output variable. And that's really the case here in our graph as well. Okay, so here I just want to take a moment to talk about interpreting graphs in the context of some sort of situation. Right, so here we have a graph with a G variable and a D variable representing the gas and the distance. If I look at a point here, I'm going to pick just a random one, but a point on the graph. What does this point mean? So this point has two different values, right? It has a G value and a D value, a horizontal position and a vertical position. And what this is really saying, this pair together is saying how much distance D the vehicle can drive with G gallons of gas in the tank. Right, so for example, if I look at the most extreme example, this point up here, if I look down and find its coordinates, right, so it's got a G coordinate of 20 and an H coordinate, or not an H, a D coordinate of 300. Right, so that's my ordered pair. That's really saying that if there's 20 gallons of gasoline in the tank, then this vehicle will be able to drive 300 miles. Right, so that's really how we can interpret the points on this graph and their relationship to the situation being described. So let's use the graph now to determine the following value. So here it says how far Corey can drive on 5 gallons of gasoline. So here 5 gallons of gasoline. This is saying use 5 as the input value, the number of gallons of gasoline in the tank, and figure out how far Corey can drive. So here if we look at our graph and we look at where we have a point with an input value of 5, or 5 for our g variable. Well, here's 5 for our g variable. We can find the point on the graph here. What's the corresponding output value, or the distance the car can travel? Well, here it's whatever this value is on our d-axis, our vertical axis. And so here, what is this amount? Well, I know that here this would be 100. And I see that this distance from 0 to 100 is split up into 4 little tick marks. So each one of these tick marks is 25 apart, right? So 25, 50, 75. So this is saying that when we have 5 gallons of gasoline in the tank, Corey can drive 75 miles. So Corey can drive 75 miles with 5 gallons of gasoline in the tank. Okay, so the next statement sort of reverses this. It says how much gas is needed for Corey to drive 225 miles. So here this amount is not an input value. It's corresponding to a distance, right? Miles. So it's corresponding to an output value, right, with our vertical axis. So we're going to start with 225 miles along our vertical axis, and we're going to see how much gas we would need, what value on our horizontal axis we would end up with. Right, so here if I start with 225 miles, right, we know that each of these tick marks is 25 apart from the next. And so here this is where 225 would be. If we start with 225 miles as a distance value, we find our point and we look at our corresponding value along our g-axis. Right, we see that the corresponding value for g is 15. And this is saying that when there's 15 gallons of gasoline in the tank, Corey can travel 225 miles. And so here, if we go back to this sort of problem statement, what we can say is that, so how much gas is needed for Corey to drive 225 miles? So 15 gallons of gas is needed to drive 225 miles. And so this is how we can use a graph to, or an interpreter graph to sort of answer different questions about the scenario the graph is representing. And so there's a little bit of language I'd like to also use here or introduce here. So this process here, where we sort of started with an input value and figured out an output value, right here maybe I'll sort of draw an analogous picture. So we had the graph here, and we started with the input value and figured out the output value. Right, so this process is called evaluating. Right, it's kind of like when we evaluate an expression, we sort of plug into the input value and we compute the result. Here we're sort of plugging in using, starting with an input value, a value from our input axis, and then figuring out the output. So if we do the reverse, and we start with the output value and find the corresponding input value, this process here is called solving. And so we'll talk about solving equations soon enough, but what we're doing here with our graph is very similar to what we would do, the values we would get when we solve an equation.